Okay, welcome to today's lesson, determining the formula of a hydrate. So sometimes you might see the questions listed as molecular formula. So that's why I put it in brackets here. Really, because molecular formula technically means exactly how many elements there are in a formula. So when you do formula of a hydrate, it'll actually be both the empirical and the molecular formula. Empirical because it's the most reduced, and molecular because it's also the actual number of atoms. Okay, so sometimes it's just shortened to formula of a hydrate, and sometimes you'll see it with the molecular out front. Okay, so we did talk a little bit about these hydrates already. They are an important piece in chemistry that we don't often discuss with you when we're making solutions and things like that. But we have to, as a teacher, we have to be really careful to know whether we're using the hydrated form or the anhydrous form. They don't react the same because of the extra water molecules. Their molar mass or molecular weight is not the same, which affects how much we put in a solution, how much we mix with water, and then it affects the concentration. So for example, when you're in grade 10, often the grade 10 teachers come to me and say, can you please make a solution of copper 2 chloride? So what you guys did in grade 10, you would have put that copper 2 chloride, which was like a greeny kind of solution, with aluminum, and it's a single displacement reaction, and it makes, on the aluminum foil, you can start to see copper forming. They switch spots, they displace the aluminum and the copper. And so when you do that reaction, if you use the anhydrous form of copper chloride, which is like a weird browny solid, you will not get the same results. So the copper chloride, the blue solution you saw, that is the hydrated form. Okay, so it does make a very big difference in the properties of the compound. So if I asked you to hydrate yourself, you would add water. Okay, so when you have a hydrate, it's always going to be an ionic compound that has a specific number of water molecules attached, and we're going to look at a way today to calculate how many water molecules there are. So anhydrous, so this AN prefix usually means like not. So anaerobic is no oxygen, for example, when you see that in science. So anhydrous means a compound with no water molecules bonded to it. Okay, so what do we need to remember? So when you're finding the molecular weight of a hydrate, then you want to add in the two waters here. So again, depending on how much work you've done, probably you're used to doing molar mass. It's like the first step, right? So we have 1 calcium, 1 sulfur, 4 oxygens in the calcium sulfate, and then there are 2 waters. So maybe you even have memorized now that the molar mass of water is 18 grams per mole because we use it so often. So you could do 2 times 18, or you could do 4 hydrogens and another 2 oxygens. So this 2 has to be distributed, okay? And all of this work, you could really just write the final answer. If you've done a lot of these questions, you'll have noticed that molar mass is sort of a given. We just kind of do it without even really, it's like writing down your data. It's like the first step in any question. Okay, so that water makes it heavier, and you get 172.172 grams per mole. Okay, so the other piece of information we need is we're going to use an empirical formula chart, but we're going to modify it a bit. So we are going to have, when you did an empirical formula chart, there was always a column for however many elements there are, and then the first row was M, or mass. The second row was molecular weight, or molar mass. And then moles, you do M over MW. And then the mole ratio, you divide by the smallest moles. We're going to follow that same procedure, but instead of elements by themselves, what we're actually going to have is 2 columns. So if you notice in a hydrate, there's always the ionic compound, and then the water is written afterwards. So what our first column when you do formula of a hydrate will always be the ionic compound. And the second column will always be water. Always, always, always. Okay? So whatever ionic compound you're given, that goes in the first column, and then the water goes in the second column. So we're going to use this chart again. Okay? So we can, because we've already looked at this concept, we're just going to get right into an example. So a 50-gram sample of barium hydroxide, BaOH2, with some kind of water molecules attached to it, contains 27.7 grams of barium hydroxide. We're going to calculate the percent mass of water to review that, and then we're going to determine the number of water molecules bonded to each formula unit, and then our final answer will be molecular formula of the hydrate, or you could just write simply formula of a hydrate. So the most common unknown variable we use in math and science is X. Okay, so that's what we're looking for there. How many water molecules are there? So part A, how do we figure out the mass of the water? Well, we're given the mass of the whole sample, and we're given the mass of just the barium hydroxide, which means according to the law of conservation of mass, whatever the difference between those, that will be the mass of the hydrate, or mass of the water. So this can often be a first step as well, even if you don't have to do percent mass like we do here, and you have to do the chart, you still need the mass of water. So sometimes people get fancy and they write ionic compound as anhydrous salt. So salt as a common name for an ionic compound, like a compound that contains a cation and an anion, we commonly call that a salt. Anhydrous because it is missing its water, right? So that, again, that AN means no water, but it doesn't matter. So 50 is how much the hydrate weighs, and the barium hydroxide itself is 27.7, which means the difference between them is 22.3 grams of water. Okay, so whenever you do percent mass, it's always the part over the whole, right? So the mass of the water divided by the mass of the hydrate. So water makes up 44.6% of the hydrated mass. Okay, so now in part B, we're going to figure out how many water molecules are bonded together, or bonded to the hydrate, sorry. So again, you're going to make, whenever you're doing the formula quantitatively, we're going to have a row for mass, a row for mass, molar mass, moles, and mole ratio. But again, the first column is always going to be the ionic compound. So in our case, it's barium hydroxide. And the second column is water. So a couple of things about this. When we get down to the nitty-gritty and we do the formula of the hydrate, the ionic compound, like the barium hydroxide, or in our other example, the calcium sulfate, should have a coefficient of 1. So it is going to be the smallest mole amount usually, or no, sorry. I mean, you don't want to give absolutes in chemistry, but for you guys, unless you're doing if we did if we could do an experiment and you got actual data that maybe had contaminants in it or something, you might get a different coefficient. But on a paper pencil task, the coefficient in front of the barium hydroxide should end up as 1, and then the water will be some kind of whole number, so you can kind of check your answer. So I'll write that down when we get to the bottom, okay? So 27.7 grams of barium hydroxide are given in the question, and we just calculated 22.3 grams of water. So again, you decide if you need to show the molar mass work. That's completely fine, okay? So we have barium plus 2 oxygens plus 2 hydrogens I don't know what barium is. And I ran out of room. Oops, times 2. And then water is 18. Two hydrogens plus oxygen. Okay, so now again, your moles is mass over molar mass. So this line divided by this line. Okay. So the mole ratio, one more time, is divide by the smallest mole amount. But like I was saying, the ionic compound, if it's a paper and pencil task, should always have a coefficient of 1. Or it's the smallest. Okay, so if you don't get that, then maybe go back and check your work a bit. Okay, so the mole ratio, so you do, I'll write out my work, 0.162 divided by 0.162. Again, there's the 1.239 divided by 0.162 is 7.6. Which that does not make sense. So again, we can round that, no problem. That is going to round to 8. If you prefer to put the approximately thing, you can do that. Okay, and then make sure again, you want to, it does say specifically in this question, state the formula of the hydrate, but don't forget to do that. Okay, so you've done all the work. Now you just have to say the formula of the hydrate is, so you've got the barium hydroxide, and then basically we solved for X. So here is the formula, okay? And you just have to put in the 8 where that X is. So you put a dot, that's the semantics of it, that's how we write it. Then you put the 8, and then you put the H2O. If you want to write a note for yourself about the rounding. It's the same thing as when you did formula, empirical formula. Okay, so pretty similar to empirical formula, just a little bit different in the chart. Okay, so a column for the ionic compound and then a column for water always when you're doing formula of the hydrate. So again, think about what hydrate means, that if I told you to hydrate yourself, you would drink water. You would know that. The homework for this section is actually from a different textbook. So you'll see a file for the blank note for this section, a file with the video or a link to the video, and then underneath will be a PDF version of the questions. I'll scan them and put them on there, and then the solutions as well. Some of the questions are a little bit wacky, so a little bit tricky. Give it a try and see if you can figure it out. Then technically it is going to be for tomorrow, where you're going to do, it gives you lab data, tries, unfortunately we can't do the real lab, and then figuring out how you can get, you can figure out the amount of hydrate left. So what you can actually do is you heat the substance that has, here we go. So it's pretty easy to do. This is exactly what we would have done here in this video. It is a test tube, and let me just see. It's a test tube, and they've added, okay, so the blue stone is the hydrate, and then when you heat the blue stone, the copper 2 sulfate pentahydrate, then what happens is it actually drives the water off and you get a white solid left over. So it's actually a really easy thing to do. You just need heat. So this person has fancily called it the thermal decomposition, which really means all you're doing is heating it up. So they're using an evaporating dish and a Bunsen burner. You can see the wire gauze there. We would have used a test tube, but it's the same difference. So you can see the blue turning into white. The reason I like to use a test tube is at the top of the test tube, you would actually see the steam in like the water droplets. So sort of proving that you're driving water off. So you would have weighed the before and the after and figured out how much anhydrous white powder was left over. Okay, so that